applying big data for understanding glacier terminus change.
Test. Okay, good. All right. Thanks, Ginny, for the nice introduction, and thank you all for joining me today. Today, I'm going to talk about how to automate the glacier terminus extraction and do it from big data based on deep learning. All right, I will move it up. Is it better? Okay, good. So first of all, why we care about glaciers? Because glaciers are important for our environment, and they are the primary driver of the sea level rise. The sea level rise increases the vulnerability of the coastal regions to flooding. And especially it is important, especially in the current context of global warming, when the glaciers are retreating in dramatic rates. And here I will show you how dramatic the glacier retreat are. So this is a map of the glacier retreat rates. The red means glaciers are retreating, blue means the glacier are advancing. And we can see that from this map, all of the glaciers, almost all the glaciers are retreating. And here's the largest glaciers in Greenland, Jakob 7. And this glacier retreated more than 40 kilometers over 1851 to 2010. And the calving mechanisms vary spatially and temporally over the whole Greenland ice sheet. And that makes this calving mechanism complex to understand. And for example, the geometry has a great influence on calving mechanisms. And based on the geometry, we have four different types of glaciers, and each of them has a distinct behavior. And because the glacier geometry varies over the Greenland ice sheet among different glaciers, that's where the spatial variation comes from. And over time, as glacier retreat, its geometry can change, and making the glacier from one type to another. And that's where the temporal variation comes from. For instance, the largest glacier, Jakob 7, it used to have a huge ice tongue, like it is in this tab, but nowadays it lost its ice tongue completely, and now it becomes a rounded glacier in the deep field water. And to understand these spatial and temporal variations, we need to have a terminus dataset that is spatially comprehensive and also has high temporal resolution. Beyond that, morphology of terminus is also important and can give us some insight about calving mechanisms. So you can see this glacier terminus is convex and relatively smooth. It means that this type of glacier is most likely driven by buoyancy forcing. But for this type of glacier termini, it has a concave shape with embedments where subglacial discharge is concentrated. And for this type of glacier, it's most likely be driven by melted water. And you can look at this purple line over here. It represents the location of plume, which is an evidence of melted water. The melted water drainage beneath the glacier and upwelling to the surface of the water and forming this plume. So to summarize, to understand the ice-ocean interaction better, we need a terminus data with full width morphology, high temporal resolution, and the complete coverage to cover all the glaciers in Greenland ice sheet. So because of the proliferation of remote sensing in recent years, we do have the chance to have this really comprehensive terminus data set. So here I list some of the operating satellite, and here's the number of images for a single glacier. So in total, we have 1,000 images for just one glacier. And considering that in Greenland ice sheet, we have around 300 of glaciers, and combine them, we will have more than 300,000 images. And it is basically impractical to manually delineate glacier termini from such a big data set, which is what we did traditionally. So we need to find a way to automate the glacier termini extraction. And deep learning provides this opportunity. Why deep learning can help? Because deep learning can learn the features by itself. When we want to recognize a person from its picture, our brain precises a lot of information before we know it, such as the face of this sheep, the haircut, the clothes, and so we can recognize, oh, this is that person. But it's hard to describe quantitatively all these features. It's the same with the glacier. So if you look at a lot of glacier images, you will know immediately which part is glacier, which part is ocean. But if you ask me to provide an equation to describe the texture of the glaciers, I couldn't do that. But fortunately, I don't have to, because the deep learning can learn the features by itself. As long as I teach the deep learning network which part is ocean, which part is glacier. Another advantage of deep learning is it has a high learning capacity. And deep learning is widely used in many complex scenarios. And the glacier system in Greenland is also complex. Different glaciers have different orientation, different geometry. Look at these 3 glaciers. They are the largest 3 glaciers in Greenland. They are all different in terms of size, geometry. And for example, this one has 2 tributaries. This one has 3 tributaries over here, over here, over here. But this one only has 1. And also, if we want to increase the sampling rate, we must integrate multiple remote sensing dataset. And this multiple remote sensing dataset introduce diversity because they're different in texture and also the value range and also the spatial resolution. So even though, so these are the 3 images from different dataset, even though over the glacier part, you can see the texture are quite different. All right, so the motivation of this whole study is to save the manual practice for delineating glacier termini. And our final objective is to automate the glacier form delineation from big data based on deep learning. So to achieve this objective, I will present the work step by step by showing this 3 stories. First, we need to design the deep learning method to automate the glacier terminus delineation, how we can utilize the deep learning to do such a thing. And second, because we want to apply the deep learning to the whole Greenland ice sheet, we must test the spatial transferability to show that the deep learning method can extract common features among different glaciers. So if the spatial transferability has been proved, we have more confidence to apply the deep learning method to the whole Greenland ice sheet. And also, we need to test the feasibility of using multiple data sets because we want to increase the sampling rate. And finally, we will apply deep learning to the big data set and extract a tremendous amount of terminus traces. So let's talk about first study. This is a startup study. So I only apply the deep learning to the largest glacier, Jakob 7. And using only 1 remote sensing dataset. All right, so the first step of using deep learning is to prepare the training data. We need to teach the network which part is ocean, which part is glacier. And how we do that is by preparing such a label image, where the positive part is white, showing the glacier region, and the negative part is ocean. All right. After we're preparing the training dataset, we start to train the network. The network training is actually a regression. It's exactly the same with regression. The CD steps. First, we need to initiate the network parameters, like the regression, and do the forward propagation, input this training image after many layers of many convolutional layers. We output something, a binary image, like this one, but not exactly the same. At first, it may be very different from this ground truth. And then we calculate the network's output with this ground truth image and use that difference, do the back propagation to update the network's parameter. And we keep doing step 1 to step 4 until the network gets to its convergence. It's exactly the same with regression. So after the network is well trained, we input this image, and then it can output something very similar to this ground truth image, telling us which part is glacier, which part is ocean. So after we train the network, we input the remote sensing image. It can give us this binary image telling us which part is ocean, which part is glacier, and then we vectorize this raster into a polygon. This is a polygon contains both terminus, which is over here, and also the image borders. We need to truncate this polygon and to get this glacier terminus. And see, here's the result of the network delineated terminus. So we compare our machine picked terminus with the human picked terminus because it is a human supervised deep learning method. The performance of the network delineated terminus can be as close as to human level, but cannot be better than that. So we can see that our results agree well with these CCI products. This is a manually delineated products. So yes, our method can reach to human level performance and see manual practice. So the highlight of this first study is that we do automate the terminus delineation based on deep learning and see manual practice, and the accuracy of the network delineated terminus can be close to human level. But there is one limitation. This method is restricted to Yakov 7, the largest glacier, and the Terrace X images. If we apply this current network to another places in Greenland using another dataset, it's not going to work. And that's what we are going to do in the next. We need to test the spatial transferability of deep learning and feasibility of using multi-sensor remote sensing imagery. First, why we need to test the spatial transferability because deep learning, if the deep learning method do have this spatial transferability, it means it can extract common features from various glaciers, and we have more confidence to apply it to a lot of glaciers. And the second, the multi-sensor remote sensing imagery can increase the sampling frequency. So how we test it? We select the 3 largest glaciers in Greenland, and Yakov 7, Kangarooswag, and Helheim. We use the 2 of them to train the network. And after the network is well trained, we apply it to the 3rd one. So it means that the network haven't seen any information of this glacier. If the network can generate some promising terminus traces, it means it can learn the common features from these 2 and apply it to the 3rd one. And the multiple remote sensing images brings us challenges because they are quite different. Those diversity, they're different in resolution, texture, and spatial, the pixel values. Here is the resolution of different remote sensing imagery. They range from 3 meters to 40 meters. And they are all showing the same glacier, but the texture, we can easily tell they're quite different. And how to solve the diversity caused by multiple remote sensing dataset. We use the histogram normalization to solve the different value ranges and image textures. And we use a more advanced deep learning network to solve different spatial resolution. So first, let's talk about this histogram normalization. So these 2 are the original remote sensing images from A and C from the 2 different datasets. And below them are the histogram of this image. We can see the pixel value range varies a lot. This one is from 0 to 2,500, but this one is from 5,000 to 25,000. So it's quite different. And also the histogram, the shape of the histogram is also different. And we can visually tell the difference between them. But after normalization, the histogram becomes a standard Gaussian distribution with exactly the same value range, and it looks more similar than before. Another important thing about the histogram normalization is that it can enhance the contrast. So this image, originally it suffered from these shadow issues, and the network doesn't have a good result over this shadowed area. But after normalization, we increase the contrast of the image, and the results is closer to reality, actually. And next thing is how to solve this different spatial resolution. We use a more advanced deep learning network. And this deep learning network has one advantage, is that it can sense information at multiple scales. So if the image size is the same, but with different resolution, when the low resolution image can cover the whole glacier, the image with high resolution only cover a part of the glacier. It's just when you look at things closely or look at things in a relatively long distance, something like that. So in that case, this advantage is really useful for us to integrating different data sets with different resolutions, because it can sense information at multiple scales. Images with the same size are actually describing things at different scales. So, and here's example of the network delineation on the third glacier. So this glacier is not included in the training data set. The network hasn't seen this glacier before, and it can generate promising results over this glacier. And over here is the name of the satellite. It changes. It means that the deep learning network can work well on multiple data sets. So to summarize this second study, sorry, one more thing. After we integrate all the we integrate multiple remote sensing data set, we increase the temporal resolution. And one benefit of increasing temporal resolution is that we can directly observe large carving events from the time series itself. If you look at this one, those little jumps, each of them represent a large carving event, right? So the glaciers keep advancing, and suddenly it retreats. It retreats a lot. There's a jump. And I will show you what happens over here. So before the large carving event, there is a 4 kilometer long crevasse. And after 4 days, this one broke and have a large carving event generating this tabular iceberg over here. So because we have the high temporal resolution, from the time series of terminus variation, we can directly observe this type of behavior. So to summarize the second study, we integrate 7 remote sensing images. With a single deep learning network, we can apply it to the 7 remote sensing data set and extract the terminus traces. And the method can be applied to glaciers that are not included in the training, proving the network has the spatial transferability, which gives us more confidence of applying it to other different places. And the integration of multiple data set offers us a sub-weekly terminus data set. Now the terminus data set has a really high temporal resolution. We can even directly observe the large carving event from the time series itself. All right, so now it's time to apply the deep learning to big data to extract tremendous amount of terminus traces. But before that, there are challenges caused by big data. The first is generalization. So the real world data is really complex. It contains a lot of different scenarios, conditions, like the weather condition, illumination condition, geometry. All of this will make it difficult for the network to successfully pick the terminus. So we need to make sure the network itself is generalized enough to recognize all these conditions and pick the terminus. The second thing is the automation level. When you are dealing with hundreds of thousands of images, any manual step during the process, any manual step can require a lot of efforts. So we must automate the whole pipeline as much as possible, from data collection to data quality control and uncertainty estimation. All the things should be done automatically. And the third thing is we need to make sure the data set itself is rigorous, because we can't manually check in the quality of individual terminus traces. We have to do it automatically and also make sure the data quality is under control. So actually these two things are coupled together. We need to achieve these two objectives at the same time. First, let's talk about the generalization. So as I mentioned before, the real world data, if we're dealing with hundreds of thousands of images, they're really complex. The real world situation is complex. It contains a lot of different conditions. And so if our training data set is more diverse, the more diverse the training data set is, the more it can represent the real world situation. So if deep learning method absorb information from this training set, so if there's an image which is totally different from what we have in the training set, it means the network haven't seen this image before. There is something is totally different from what the deep learning method have learned before. So in this case, we can't expect the deep learning to give us a reasonable results. So that's why we need to make sure the training set is diverse enough to match the real world situation, to make sure the deep learning method learn everything it needs before applying to the big data. Unfortunately, we can have this highly diverse training set because scientists have been picking Terminus data manually for decades. So we do have a lot of human-picked Terminus traces. And here's a study published by one of our PhD students, Sufi, on cryosphere. It is a highlight paper. I'm sorry. All right. It collects basically all the existing manually picked Terminus traces. One of the advantages of this data set is that it has a large number of traces and it covers various conditions, weather, illumination, orientation, geometry, and different sensors, so on and so forth. So it can help us to build a training set with high heterogeneity. But the problem is that the Terminus traces in term peaks are the curves, like this right one. What we need is a label polygon, a label figure, with white part showing the glacier and black part showing the ocean. How can we make such a conversion? We need to prepare a reference polygon, which is the blue polygon showing here. It covers the whole image, right? And with its terminus is behind all the traces in the term peaks, right? By replacing the terminus in this reference polygon with these traces, we can generate new label polygons and then converted them to the label figures. So that's how we automatically preparing the training data set from the term peaks. And then we need to automate things. The first thing we need to automate is data collection. We have this platform called Google Earth Engine. It has 5 remote sensing data sets. And by using this platform, we can automatically collect images on this platform. So because we are dealing with hundreds of thousands of images, if we use the traditional way of downloading images, sitting in front of the computer and clicking on the website, it might take months just for collecting images, which is horrible. So we have to find a way to automate it. What we need to do is to prepare a region of interest. That's apparent because we have to tell the platform which part we are interested so that it can filter the images, gives us what we want. And another advantage of preparing this region of interest is that it can save storage and processing cost. So a full remote sensing image is around 800 MB. But after cropping it to the region of interest, the image size will be less than 10 MB. So in total, we collect 430,000 images and with a total volume of 1 TB. So this is the cropped image. We can crop image on the platform. This is the size of the cropped image. So you can imagine if we don't do the cropping, how large the data set will be. And second thing is that we have to automate the data quality control. It's extremely hard to make the deep learning method work on all the images. It's extremely hard. And I cannot give such a promise that deep learning will work on all the images. And if we want to further increase the deep learning's accuracy, we need to manually prepare more training data, which requires a lot of efforts. So it is more cost effectively to build a screening module to filter out some results with bad quality. And although the deep learning network cannot work on all the images, it can have a good performance on most of them. And based on that, we use this interquartile range to calculate two thresholds. One is a lower threshold, one is upper threshold. So anything beyond these two thresholds will be taken as an outlier and will be thrown away because most likely they have bad quality. For instance, if the terminus traces are of good quality, the lengths should be similar to each other. So if there is a traces with a extremely short length or extremely long length, there must be something wrong with these traces. So let's give an example. So we measure three different things: the length, the curvature, and error formed with its adjacent peaks. So length is easy to understand. For example, this one is too short, this one is too long. And for the curvature, if all the terminus traces with good quality are relatively smooth, then if there's a terminus traces with really complex shape, then there must be something wrong. That's what the curvature measures, the smoothness of the terminus. For example, this one, the shape of this terminus is really complex. So it will be detected by our screening module and throw away. And also, the third one is the error formed with its adjacent peaks, the temporally closest one, because we have a high sampling frequency, right? In that high sampling frequency, we will expect the terminus to behave regularly. There's no sudden changes within that short time period. So if the error formed with its previous terminus peaks is quite large, then our screening module will detect it and consider it as an outlier and remove it. The third thing we will need to do is to automate the uncertainty quantification. Traditionally, we measure the uncertainty by comparing the machine-picked terminus with human-picked terminus. So if we want to measure the uncertainty in traditional way, we need manual efforts. Because deep learning method can have various performance over different conditions. Like when there's cloudy, the accuracy may be lower. When there's shadow, the accuracy could also be lower. So overall, it varies among different glaciers over different conditions. So if we want to make the uncertainty measurement representative, then it means in traditionally, we need to put a lot of manual efforts to do the manual delineation. We don't want to do that. So we need to find a way to automatically quantify the uncertainty. There are two ways I use. One is use this duplicate traces. The other is called Enze dropout. The first thing is, let's talk about the duplicate traces. Because we're integrating multiple remote sensing data sets, there are dates that has more than one remote sensing images, means we have more than one traces. We can measure, and all of them are measured, are picked by the terminus, are picked by the deep learning network. We can quantify the error between the traces from different satellites on the same date. So for example, this blue one is from the Landsat 8, and the black one is from the Sentinel-2. Both of them are picked by the network, and they're quite different. So by measuring the difference between them, we can quantify the uncertainty. The second thing is called Enze dropout. Enze dropout can yield variance of network by randomly setting a part of the network's parameters as 0. So because of this randomness, it can give us a variance of the network. And we can use this variance to make multiple predictions on the same image. And by measuring the difference between these multiple predictions, we can quantify the uncertainty. So if the original, this right curve shows our original prediction, and the other colors shows the output of the MC dropout. So if the original prediction is good, then the MC dropout will be close to the original prediction, like this one. And although they are not exactly the same because of the randomness of the MC dropout, but if the original prediction looks funny, like this one, the output of MC dropout will be deviate from this original prediction, and thus the uncertainty will be large, measured by this one. All right. So after all the things, generalizing the network, automate the data quality control, and measure the uncertainty, the deep learning method can finally handle the diversity caused by big data. So here is the results of the machine picked terminus. It can cover different situations. Here is the cloudy Landsat image it can pick, and the Sentinel-1 image with asymptote in winter. So in winter, when there is asymptote, the terminus, the boundary over here will be blurred, but our network can successfully pick the terminus traces. And also here's a cloudy Sentinel-2 image, and here's the image with shadows. And over here is the terminus with small features, can also be tracked by our deep learning network. And even for this one, the Landsat 7 with this strip-like gap, our deep learning network can also pick the terminus. All right. And here's the time series of variation. We can cover a long time span with a high temporal resolution because of the data fusion. We integrate multiple data sets. And also, you can see these crosses over here is the wrong terminus traces detected by our screening module. If you look at closely up to 2013, this is comparison between our results and the other data sets. So this is the right circle represent the term picks, the manually picked terminus data set. And this one is Coffin, another terminus data set picked by machine. So we increased the sampling frequency a lot by including the Sentinel-1 images and Sentinel-2 images, because for this Coffin data set, they only focus on Landsat images. And here is another figure showing how successful we are, and the left figure showing the number of images on the over different glaciers. They have spatial variations because of the satellite coverage can vary among different places. And over here is a successful rate of our method, because we have this screening module. Some of the traces has bad quality and will be detected by it and will be thrown away. So here's the successful rate of each glacier. The darker it is, the higher the value will be. So basically, overall, our successful rate is quite high. Satisfying. And here's another figure showing that our terminus picks basically covers all of the images. So these orange dots means that we have the terminus traces, means the dates that we have terminus traces. The black dots means the dates that we have the remote sensing images, but the traces has been removed due to the low quality. And the abandon of some results could be due to the image quality, and also could be due to the imperfection of the network. For instance, over here in winter, for this glacier, we remove a lot of traces because, again, in winter, because of the existence of asymptote and snow cover, it's really hard to tell whether the terminus traces is. And even for me, when I look at the remote sensing images, I don't know precisely where the terminus traces is. So it's hard also for the network to decide where the terminus is. All right. So the conclusion is that we design a fully automated pipeline that can continuously produce terminus traces, because everything within the pipeline has been automated. We don't need to do any manual efforts. We just need to click the button, let the script running. And we have produced 279,000 images, termini, with quality being controlled and uncertainty being measured. And we call this data set as auto term. So the auto term can be beneficial to the community for conducting a pan-Greenland investigation on terminus variation, no matter it is on a seasonal cycle, or no matter the investigation is about the seasonal signal or internal signal, because we do have a comprehensive spatial coverage and also high temporal resolution. All right, the future work, because I have generated the time series of terminus variation for a lot of glaciers. Next step, I want to look at this time series and trying to find some interesting story about the seasonality of the terminus variation. Different color, by the way, different color represent the traces from different remote sensing imagery. And at the end, I would like to mention about the potential of supervised deep learning. This is the method that I used. So in general, it can be applied to feature extraction or identification. The feature are apparent, like a person we know who is, or a cat image, we know immediately that this image is about a cat. So the features should be apparent, but it won't hurt if some experiments are needed. And the work needs to require a lot of labor. That's where deep learning can help to automate things. So this part is actually a human supervised deep learning. Oh, oops. So it means that we human beings prepare the training data. And the second one is it can be an alternative to a high cost model. For this one is a model supervised deep learning. We use the output of the physics-based model to train a deep learning network. For this one, the advantage of using deep learning would be make the calculation cheap. So for sometimes a physics-based model can take months to make this simulation, but if the deep learning is trained by that, it may take several seconds or several minutes to make the prediction. So sometimes it can make the calculation cheap. But overall, if you have any idea about that deep learning can help with, please feel free to talk to me and let's explore some potential collaboration possibilities. Thank you.
All right, I'm happy to entertain questions for Enze. Duncan? Oh, Michaela.
Sure.
I have a question. So knowing like the various spatial what is like considerably a good training set? Like, because I know you can get to get it like that. So like, what, like how
yeah, the good thing, that's a good question.
Can you repeat the question?
Oh, okay. So the question would be, what makes the training set good? How many glaciers that the training set need to cover? How many situations it needs to cover? The answer is, I don't know. The more, the better. Because the more data we have, the more comprehensive the training set would be, and the more it can represent the real world situation. And accordingly, the network trained by the training set will have a higher accuracy because it has learned more information from the training set. The more, the better. But another thing about preparing the training set, it needs manual practice, right? If it's a trade-off. If you want the training set to be comprehensive, you will need a lot manual efforts, and also the time caused by training the network will be longer. It's a trade-off.
Thanks. Yeah, very interesting talk. So is there any signal in your noise? You've got the things that you're rejecting. Are you able to learn anything from the bits that you are rejecting, is there anything systematic in that you've been able to pull out? Obviously there is the seasonal aspect with the illumination, but are there other things going on there?
You mean the terminus variation? Is there anything?
The images that you reject from being able to actually use them.
Oh, okay. So let's look at this this figure. So this figure are actually the images that I reduced. Well, there are two reasons that I remove the data with remove the results with bad quality. One is image quality. The original image quality is bad. A human being cannot be able to tell where the terminus is, like this one. It's heavily clogged, so we don't know where the terminus is. So it's expected that deep learning won't know either. And another thing is imperfection of the deep learning method. For some images that we human being can tell where the terminus traces is because the training set is not comprehensive enough. It didn't learn enough information to make the deep learning network generate promising terminus on this specific image. Sometimes it both can cause the traces have bad quality. Right. Oh yeah. This one.
Red axis. And so this is the glacier. You can see it's like 4 5 meters. It's very unlikely that thing has advanced 4 kilometers.
It's very unlikely that is actual reality. Maybe some of the X's that are really close to the mean position, but the stuff that's really out there is very unlikely. And I don't think, Enze, you've had time to go and look at all the X's and see all the abandoned traces and see. We just have too much data to really do that.
That's why we have to make everything automatic.
Hey, quick question. Good talk. Can you go back to the previous slide you were showing about the 3 criteria for quality control? Yeah, that one. I have a question about the area one. I understand the reason behind it. When you notice a huge area between the current one and the previous one, obviously wrong. But on the other hand, isn't this sudden change what we care about the most? Say for Antarctic ice shelves, we care about the sudden collapse of big ice shelves.
Question. That's a really good question. So actually, in reality, this can happen. So because, as I mentioned here, there's a large calving event. So within 4 days, there's a jump. So that's why it is not just about the. It's not just about the area formed with its adjacent peaks. We actually look at 5 consecutive peaks. We quantify the area formed with its adjacent peaks. So there's another assumption that this big calving event can't happen too frequently, right? Within 10 days, there can't be 2 large calving events. That's not possible. So if we look at 5 consecutive dates, there will be only 1 large calving event. So if I look at a series of 5 consecutive traces, if there is more than 1 large number, I will remove this. If there's only 1 large number, I will keep this and take it as a large calving event.
Thanks for the talk. This is a little bit the same question as Duncan's, in the sense of, does it make sense to try some like physics-based rule-based rejection criteria, right? So where, Ginny mentioned you don't expect these large jumps, right? But maybe there are other things that you can turn into simple rules about, I don't know, this line being convex or concave, this line moving only in one direction, sort of simple stuff where you could apply that, and that not necessarily because it's true, but because you can see where what would be rejected, and maybe that's telling you something about the degree to which these assumptions hold. It's again like trying to get to sort of the noise, but having some sort of rules in there and checking if they work or not.
Yes, I think that's a good suggestion. So it will be good to have some physics-based rules.
The threshold of the length of the chart and the change in the area of the student, it's not physically usable. Those are actual physics-based, physically.
Yes. And another thing about physics-based is that different glaciers have different mechanisms, and because of this, there's differences among them. We have to be specific, and when we automate things, we want things to be more general, that can be universally applied to all the glaciers. We don't want to have a law different for different glaciers, so on and so forth.
Right,
So-
but you apply the same rule, right, to inflation, like 100%.
Uh-huh.
When-
Yeah, that will definitely show something. It means that this glacier has another law to govern these covering mechanisms. Yes.
The convexity though actually like with and so we wouldn't use that with something that's what we want to do is use the determinant ontology to fit the process. So now we have the data and ontology and able to infer
I early on, I saw that your termini included, it's a three-body problem, right? It's not just ocean and ice, there's bedrock in there too.
Yeah.
And that wasn't explained to me. I mean,
Okay.
some of that is not going to move over multiple images.
That's true.
And then later in the talk, you only showed the boundary between ocean and ice. So I'm a
Okay.
little confused there. I mean, if you see a boundary that doesn't move, do you know that that's a boundary with rock?
That I will explain this. So it is true that we didn't separate the glacier and bedrock, and also true that we extract both glacier termini and fjord boundary, like over here. But actually, as you mentioned, this part doesn't move, and we have a second way to further truncate this.
So you can see the difference between, you recognize in your learning process, the difference between a piece that isn't moving and a piece that is. These termini only show the boundary between ice and ocean.
Yeah.
Early in the talk, you showed me boundaries that included
Yeah.
boundaries in the fjord with rock.
All right.
And that to me was a transition I didn't.
All right. So you can see,
There.
right, this part, you can see this part is actually the terminus, the boundary between us and the ocean, and over here, this part is actually the fjord boundaries. We do several processes. So originally it is a polygon, right? It contains termini and the fjord boundary and also the image boundary. We truncate it first, have a truncating boundary to have this curve, and also we also use the boundary of the bedrock to further truncate it, because we only care about the boundary between us and ocean. Oh yeah, one of the advantages of our data set is that it can be updated, the S-mask. So the S-mask has been used to quantify the elevation, the S-mask loss by using the elevation data. So the S-mask is important because we know which part is glacier, which part is ocean. So in this case, we won't distribute the mass loss over the ocean, right? But as the glaciers are retreating and in a dramatic rate, so one of the advantages of this terminus data is that it can update the S-mask. So now the S-mask can be updated annually, and each of the year we know more precisely where the ice is, where the ocean is.
I guess I have a follow-up to Jamie's question. I can envision in the mass loss, but also in trying to go from an interesting geometry of your terminus
Mhm.
to the boundaries of your glacier, that's another fairly complicated process. So that bedrock ice contact, which also involves a narrowing that may not be exactly reflected in the length of the terminus, right? Because the terminus can be complicated, yet the whole mass size could drop down. Is that something you got? Yeah, in other words, as it drops in elevation, it might narrow in extent, right? All of which equals mass change, but it might not be one-to-one with what's exactly happening with, say, the length of the terminus. If you understand what I mean.
You mean the length as the glacier retreat, the length of the terminus could be smaller and smaller because the
Yeah, or it could get quite complicated, and the actual length of the terminus could be quite convoluted as it goes into a melt stage, right? And that the overall length of that red line in that picture doesn't necessarily correlate with the narrowness of the glacier. So I'm just curious if you've thought about an extension to this where you're going to try to go for the width of the overall tongue of the glacier within your images as an additional data point.
This is actually the things that changing that I worthwhile boundary.
Right. It's following up on what James.
Well, at the beginning, I do choose the field one boundary.
But then you aren't, you're only using it for the terminus. That data of that,
Yeah, because
that's important data. That's my point.
Right. In the future, if I want to use the field boundary, I can add it, do some more analysis about the geometry of the terminus. But currently, why am I removing this field boundary part? Because sometimes the field work can be really complex, and the network doesn't have a good performance over the field work. So, but it has good performance along the ice ocean boundary. So I want to keep them and remove the artificials caused by this wrong results over the bedrock field, the field boundary. Right.
Okay, I have another theoretical question. So would you say you're like far off from like changing this from like a terminus position based study to like understanding calving events? Like maybe how much work would it be to go back and be like, okay, this data set can help us see like which glaciers have major calving events? I guess comparing like all the data sets and terminus changes that you have.
Yeah, we do have such ability. So if you look at the if you look at this time series, oops, sorry. All right, if you look at this time series, there are jumps. So by setting a threshold, by setting a proper threshold, we can immediately tell how many calving events it has for this glacier during a period of time. Right. Right.
Blow up of the top, right? And the top has a lot more data frequency when we get to like 2014. That's when Sentinel-1 was launched. And so we really probably can only do calving events from 2014
Yes,
onwards.
that's true.
For
That's
glaciers where Sentinel-1 actually works. It randomly doesn't work for some glaciers because of this stupid positioning error that it has. But yeah, we think now we can do calving events from 2014 onwards.
Yeah, at least after 2014, we can do such a thing. You mean over here or here? Oh, okay, sorry.
Oh, we just haven't, I mean, we haven't looked at the characteristic pattern changes really
We
to be
haven't
able to
really looked
interpret
at-
it.
Yeah,
This is the first time we've had this much data other than having in situ cameras or something. All right, well, if there's no more questions, if anybody wants to join us for lunch, we're going to meet outside of our pod at noon. Otherwise, I'll see you around UTIG.
thank you for helping me with those questions.
Yeah, no worries.